Good morning, everyone. Today, we are going to be reading the three postulates of quantum mechanics, and this is just something I can take a little break from studying the GRE from, and I think that'll be nice. We're not going to explain them at all. We are simply just going to read the postulates, and anything that comes after that will have to be in future videos. So what is a postulate? Because that can be a pretty fancy word, and it's really just an idea or rule assumed to be true for the sake of that theory. In terms of quantum mechanics, since quantum mechanics is such a relatively new theory, how do you explain certain laws, certain things in nature, certain phenomena, that we may not fully understand yet, but by having the rules for those, we can set up a basis on how to come up with new theories and new ideas to explain these laws of nature. Alright, so let's define postulate 1, but before we do so, I do want to explain that if at any point you don't understand what I'm saying, don't worry too much about it, because I really don't understand what I'm saying, but just by recitating the postulates doesn't mean I have an understanding myself either, but it means that in future videos, I'll be more determined to answer these questions and follow these rules. Let's begin. Associated to any isolated physical system is a complex vector space with an inner product that is a Hilbert space. This is known as the state space of the system. The system is completely described by its state vector, which is a unit vector in the system state space. And if you don't understand what vectors are, vectors are pretty much ways of describing coordinates, movements, directions, and so on. So why is this important? What does this all mean? It's because quantum mechanics is commonly tied to linear algebra, and not like normal linear algebra. Or if you don't understand what I'm saying, I'll attach a book below that you can actually read, which I found was very helpful for my theory of linear algebra class. What it deals with is, how do matrices work in describing our relations to coordinates and coordinate systems and inequalities and so on. And believe it or not, quantum mechanics uses this all the time. I'm into linear algebra here and there, so I'll actually cover some of the topics in that book throughout my series. This book actually focuses, the book I'm reading right now, the Quantum Computation, Quantum Information book, focuses on linear algebra solely for the almost first third of the book. That's how important linear algebra is to quantum mechanics. So if you don't fully understand it yet, don't worry. We'll be covering a lot of it, because even though I have an elementary understanding of it, I can always improve that understanding before we get into the deeper quantum mechanical ideas. Okay, so before diving into postulate 2, it's worded a little bit confusing, and what I'm trying to say with the linear algebra thing is, when a state V of a quantum mechanical system transforms over time, or we transform it over time, how do we predict those consequences, right? Because all mathematics is predicting the consequences of nature and having that tool set ready for the future or any other situation you decide to apply. While some of the ideas you learn in mathematics might not be applicable to everyday life, having that tool set only makes you more ready. Postulate 2 states the evolution of a closed quantum system is described by a unitary transformation. And without diving into the mathematical model of it too much, because I want this to be something you can solely listen to, when we transform the original matrix, can we predict what the next matrix will be? Can we predict what the next quantum mechanical system or state will be, and how it will change, and what those consequences are? Heisenberg's principle, whatever, states that measuring a quantum system will actually result in a peak of that system, which will collapse any measurement you make. And this is because quantum mechanics moves faster than we can possibly measure with a classical computer. So in order to understand quantum mechanics, we have to give up the idea of being able to measure it, because it comes down to prediction. And so how can we predict the change of something or some vector space? And how can we predict that changed vector space is the original vector space, right? So if I have this random vector space that I know has been transposed or worked on somehow, how can I find the original matrix underlying it? How can I find the original vector space underlying this matrix? This is actually perfect, because postulate 2 and how I explained it sort of leads into postulate 3 of quantum measurements. And quantum measurements can be described by a collection of measurement operators acting on some state space of the system being measured. I don't understand what this postulate means too much, and without diving into a mathematical approach, this is where we will end this video. And hopefully by the next video, I better understand how to explain this postulate. But, to generally or vaguely describe it, what it means is that we can describe quantum measurements, and although we can't fully understand the specific measurement of each quantum state, quite physically, we have the ability to predict some of the consequences that occur in quantum mechanics. Thank you guys for watching. I hope you enjoyed this video, and obviously, as I continue to understand it more, I will continue to teach it better. Have a good one.